Dear students, with this now let us move towards the molecular weight concept of the polymers, right? So molecular weight of polymers, right? See here, so in our chemistry there are two extremes of the subjects are there. So in one extreme, so if you go down the size, the properties are going to change. So that is called as nanotechnology or nanoparticles, right? So it is because of the reduction in the size, right? Size of the nanoparticles, the properties are going to change drastically, right? What happens when a molecule moves from bulk to nano? So the total value remains the same, but the collective surface area greatly increases, right? So it is because of that reason nanoparticles are start to show excellent properties. So similarly, there is on the other hand, there is another extreme, so wherein if you go up the size, the properties are going to change, and that particular extreme is our polymers, right? So in case of polymers, it is essentially because of the gainedness, or it is essentially because of the very high molecular weight of the polymers, the properties are going to change, right? So compared to low molecular weight compounds, the polymers exhibits excellent properties. It is all attributed towards the molecular weight, right? So for instance, if you can consider a simple low molecular weight compound, right? So in case of a simple the molecular weight can vary from a single digit for a simple low molecular weight compound to a number, it is in millions for a polymer, right? So say for example, the molecular weight of hydrogen is only 2, right, while that of circular DNA in E. coli is around 2 billion, right? So that means that, so when a molecule moves from low molecular weight compound is converted into polymers, the molecular weight is going to change drastically. So almost all the properties are attributed to that molecular weight. So this is the concept. Actually, here in this case, so if you compare with a low molecular weight compound, right? So a low molecular weight compound molecular weight is fixed. It is invariant of the conditions of the reactions, whereas the molecular weight of the polymer is not fixed. It is depending upon the conditions of the reactions or type of the reactions or method of polymerization that you have prepared, right? So that means that, so low molecular weight compound has a fixed molecular weight, right? Whereas polymers does not have a fixed molecular weight. It depends upon the method of preparation, right? So like this, if you can, in order to explain this very effectively, I will take an example of acetone, right? See, as we all know that the molecular weight of acetone is 58. The molecular weight of acetone is 58, right? Regardless of how it is made, right? If this 58 changes to 60, this is no longer acetone, it may be acetic acid, right? It may be another compound, and that is called as acetic acid. Moreover, so each molecule of acetone are having a same molecular size, right? So that's why they are having a same molecular size. So that's why this is true for almost all the low molecular weight compounds. So there is thus some definiteness in the molecular weight of these simple low molecular weight compounds, right? So when you come to polymers, on the other hand, so when you come to polymers, so what happens is, so it comprises of molecules of different chain lengths or molecular weights. So hence, so its molecular weight is expressed in terms of average value, right? We will not get a definite molecular weight. It is impossible to determine the actual definite molecular weight of the polymer. So why? Because it comprises of molecules of different chain lengths, right? Different sizes, right? So in order to explain that, I will take an example of ethylene, right? A simple low molecular weight compound that is called as ethylene. As you all know that its structure having a chemical structure of CH2 double bond CH2, and its molecular weight is 28. It has a fixed molecular weight of 28 in whichever the method you have prepared, right? So the problem arises is when this ethylene is polymerized to polyethylene, then the structure is going to become unknown, right? So the size is going to become indefinite. So like this, so when polyethylene is polymerized, so it will become the form CH2 N times. So we will come up with some indefiniteness about the molecular weight of the polymers, right? Whereas here the molecular weight is fixed, that is 28. Whenever it is polymerized, the number n can vary from any number to any number, right? So there occurs an indefiniteness. So why it is going to happen so is, see, during polymerization what happens is, so different chain lengths are going to start at any instance of time, but chain termination is a random process, right? So chain termination is a random process, so that means that different the chains will start at any particular instant. During polymerization, different chains are going to start at one particular instance, but during chain termination, as it is a random process, so all the chains will not get terminated at one particular point, right? So that's why we will have different set of polymer chain lengths and different molecular weights. So this can be explained by taking these cases, right? I will take this case and I will explain, so that you will come to know why for polymers we have to go for average molecular weight, why it is not possible to determine the actual molecular weight. So if you can take this RCH2 R, so then what happens is, if the degree of polymerization is 500, so likewise you can take CH2 R, and this is 550, and RCH2 R, this is 600. So if you look at the molecular weight of this polymer chain length, so it is same. The molecular weight of this polymer chain, it is 14,000. So if you look at the molecular weight of this polymer chain, it is 15,400, and if you calculate this molecular weight using this degree of polymerization, it is 16,800. So what we are seeing here is, right, so all these polyethylene chains are having different sizes and different molecular weights, right? You can look at this chain, this polyethylene chain is having 14,000, this is having 15,400 molecular weight, and this is having 16,800 molecular weight, right? So the molecular weight and the size is of different polymer chain lengths is different, right? But yet they are all very much polyethylenes only. Even though the molecular weight changes, they are all polyethylenes only. They consist of n number of polymer chains of different sizes and different molecular weights, right? Whereas in low molecular weight compounds, there is a definiteness in the molecular weight. If a molecular weight, if a number changes from 58 to 60, it is no longer acetone. So here we can see that the three molecules, right, have different sizes and having different molecular weights, and yet they are all very much polyethylenes. That's what I told. So it is because of that reason, say a polymer sample can be therefore thought as a mixture of same chemical type but different molecular weights, right? So in this particular situation, so the molecular weight of the polymer can be viewed statistically, right, and can be expressed as an average value of the molecular weights, right? It is highly impossible to determine the exact values or absolute values of the molecular weights. In contrast, the molecular weight of the simple non-molecular weight compounds such as ethylene or acetone is fixed, right? Whereas the polymers are not fixed. It is because it consisting of different polymers of different chain lengths and different molecular weights. Okay, now we can take up the average molecular weight concept of the polymers. I already explained why average molecular weight concept of polymer, it is not highly impossible to determine the absolute values of the molecular weight. So it is because polymer consisting of molecules of different chain lengths, and hence it is expressed in average molecular weight, right? So there are two most common and experimentally verifiable methods are there in order to determine the molecular weight of the polymers. So one is number average molecular weight, right? The first method is number average molecular weight. Number average molecular weight, and it is designated as Mn bar. right? So the number average molecular weight can be defined as it is the mass obtained when the total mass of all the molecules of the sample is divided by total number of molecules, right? It is the mass obtained when the total mass of all the molecules of the polymer sample is divided by the total number of molecules, right? If n1 comma n2 comma n3 are the number of molecules having the molecular mass m1 comma m2 comma m3, then its number average molecular weight can be expressed like this, right? So mn bar is equal to its number average molecular mn bar is equal to, so n1 m1 plus n2 m2 plus n3 m3 plus so on, divided by n1 plus n2 plus n3 plus so on. So in other words, we can write this as mn bar is equal to summation of ni mi divided by summation of ni, right? It is the mass obtained when total mass of all the molecules of the sample is divided by the total number of molecules. And the next method is weight average molecular weight, right? And it is designated as MW bar, right? So this weight average molecular weight of the polymers can be defined as it is the mass obtained when sum of the products of the total mass of a group of molecules and their respective molecular masses is divided by total mass of all the molecules of the sample, right? So here if m1 comma m2 comma m3 so on are the masses of the molecules having molecular mass m1 comma m2 comma m3 respectively, then weight average molecular mass can be given as the MW bar is equal to m1 plus m2 plus m3 so on divided by m1 plus m2 plus m3, right? So where m1 is equal to n1 n1, where m1 is equal to n1 into m1. So if you substitute this value here, so this equation becomes, so mw bar is going to become, so m1 into m1 square plus n2, so here, so m2 is n2 m2 and n3 is n3 m3. If you substitute all these three values here, it will become like this: n2 m2 square plus n3 m3 square plus so on. So that divided by n1 m1 plus n2 m2 plus n3 m3 so on. So in simple words, this weight average molecular weight can be given as the summation of ni mi square, that divided by summation of ni mi. So whereas number average molecular weight is summation of ni mi divided by summation of ni, here weight average molecular weight is summation of ni mi square divided by summation of ni mi, right? So it is the sum of the products of the total mass of group of molecules and their respective molecular mass divided by total mass of all the molecules, right? So as it is divided by total mass of all the molecules, right, the weight average molecular weight for all the synthetic polymers is always higher than that of number average molecular weight, right? For all synthetic polymers it is higher than that of the number average molecular weight. If that has to be become equal, then each and every molecules of the sample should be of same size, that is homogeneous, and that will never be achieved in case of polymers. And both these number average molecular weight as well as weight average molecular weight are expressed using the unit gram per mole, right? So during solving numerical problems we are going to use that unit, right? So based on this average molecular concept you have numerical problems, right? For that you need to remember these two formulas and their unit, that is gram per mole, right? So dear students, now let us take some numerical problems on the average molecular weight of the polymers. So this is one sample example I have taken. So the numerical problem is like this. So in a polymer, say 20% of the molecules, right, have molecular mass 15,000 gram per mole, and 45% of the molecules have molecular mass 25,000 gram per mole, and remaining molecules have molecular mass 27,000 gram per mole. So we need to calculate both number average molecular weight and weight average molecular weight, and after that so we have to calculate polydispersity index, right? So this is the numericals. So this type of simple problems only they are giving in the final examination. So first what you have to do is first write the formula. So because for writing formula you will be getting 1 marks. So first let us take for number average molecular weight, that is Mn bar, and its formula is summation of Ni Mi that divided by summation of Ni, right? So as they have given 3 molecules of different sizes and different chain lengths, so we need to extend this formula up to N3, okay? So that will be like N1 M1 plus N2 M2 plus N3 M3. So that divided by N1 plus N2 plus N3. So this is the number average molecular weight formula, right? So now, so before substituting to this you need to take up the data, right? So what and all data we want? We want N1, N2, N3 as well as M1, M2, M3, right? This is a simple numerical problem wherein they have given all the data. Simply you need to pick and substitute into this so that you will get the answer, right? So now let us take the data. So what is N1 here? So N1 is, they have given 20% of the molecules, right? So that's why N1 is equal to 20, and similarly M1 is 15,000, right? So M1 is 15,000 gram per mole, and N2 is, it is 45% of the molecules. So that is N2 is 45. So M2 is, the molecular weight is 25,000 gram per mole. And similarly you have to choose N3. So very wisely they have given, what they said is remaining molecules have the molecular mass. Remaining means, so 45 plus 20 it is 65, remaining out of 100 is, it is 35. So then 35 is the N3 value, and M3 they have already given, it is 27,000. Okay, so now we are ready with the data. Simply you need to substitute to this equation so that we can get the value, right? So if you substitute the value of N1 here, that is 20, then into 15,000, 20 into 15,000 plus 45 into 25,000 plus this 5 plus 35 into 27,000. Okay, so that divided by 20, N1 is 20, N2 is 45, N3 is 35. Okay, so if you solve this, so you are going to get the answer, and that answer is 23,700 gram per mole, right? So in this way you need to calculate the number average molecular weight. So now let us move towards calculating the weight average molecular weight. So that formula is MW bar is equal to summation of Ni Mi square divided by summation of Ni Mi. Right. So as it is a 3 different polymer chain lengths are there, you need to extend this formula up to 3 numbers. So that is N1 M1 square plus N2 M2 square plus N3 M3 square. Right. So that divided by N1 M1 plus N2 M2 plus N3 M3. Right. So this is the formula. So you need to must and should write the formula. Don't go to substitute directly into this, because for formula they were kept 1 marks. Right. So if you substitute all these values here, so I will start from this place. Okay. So N1 is 20 into M1 square. M1 means 15,000 square. You need to do 15,000 square plus. So M2 is 45 into 25,000 square, right, plus N3 is 35 into 27,000 square, right. So that divided by, so this number, so that divided by this, right. You already have taken it in the number average molecular weight. You can simply substitute the same. So that is 20 into 15,000 plus 45 into 25,000 plus 35 into 27,000, right. So if you do the simplification and calculate, so then you are going to get the answer. So that is around 24,531, right, 0.6, 24,531.6. So in this way, in a simple way, you need to calculate the weight average molecular weight, right. So and the unit, don't forget to write the unit, and that is gram per mole. Okay. So now the question is not yet over. You need to calculate the PDI, and you need to comment on that polydispersity index. So that is we already calculated. PDI is, it is the ratio of weight average molecular weight divided by number average molecular weight. So you have to substitute, so both these values over there, and if you do the dividing this weight average molecular weight by number average molecular weight, you are going to get, so that is 24,531.6 divided by, so 23,700. So you are going to get polydispersity index around 0.13, right. So as I already said, for all synthetic polymers, see, for all synthetic polymers, so this is about polydispersity index. So for all synthetic polymers, right, so the polydispersity index is always greater than 1. So as this is almost near to the 1, this polymer system is less polydispersed in nature, even though it is polydispersed, but the extent is somewhat less. Yeah. So this is the answer, right. So now substitute all the datas here. As straight away I am going to take substitute the values. You already know that it is a 3 component system. So 40 into 12,500 square, right, plus 30 into 25,000 square plus 30 into 31,250 square, right, that is N1 M1 square, N2 M2 square, N3 M3 square, right. So that divided by N1 M1 plus N2 M2 plus N3 M3, so that is 40 plus, right. So 40 into N1 M1, 40 into 12,500 plus 30 into 25,000 plus 30 into 31,250, right. So if you simplify and solve all these steps, right, so you are going to get the answer, that is 24,000, so 821 gram per mole, 21,000 24,821 gram per mole. So in this way you need to calculate. So this is somewhat different, so don't ever get confused with this one. This number always, this n is the degree of polymerization. The percentage if they have given means that is the value of n, right? So that is the problem.